Good evening to all. Today we have to discuss about electrochemistry. In electrochemistry, we have standard hydrogen electrode. Standard hydrogen electrode, that means it consists of platinum foil that is connected to a platinum wire and it is sealed with a glass tube. And also hydrogen gas is passed through the sides of the glass tube. Then the platinum foil is placed in hydrochloric acid. That means the cell is a device which consists of electrodes, and electrode is placed in an electrolytic solution, that is the cell. Here standard hydrogen electrode consists of platinum foil and also connected with the platinum wire and is placed with standard hydrochloric acid solution. Standard hydrochloric acid solution, that means the electrode is a standard hydrogen electrode. It can be represented as platinum H2 of 1 atm pressure and H plus of 1 molar concentration and E0, that is equal to 0 volt. When the electrode is act as anode, oxidation reaction will take place with liberation of electrons. That can be explained by H2 that forms 2H plus 2 electrons. When this electrode is act as cathode, the electrode reaction can be written as 2H plus 2 electrons that forms H2. That means the reaction is a reduction reaction with gain of electrons. Then next one is calomel electrode. So calomel electrode, that means it is also one of the secondary electrode. It consists of mercury at the bottom over which mercurous chloride is placed. The remaining portion of the tube is filled with a saturated KCl solution. The bottom of the tube is sealed with a platinum wire and the sides of the tube is opened to fill the KCl solution from it. The electrode potential of calomel electrode is 0.2422 volt. The cell representation is Hz to Cl2, KCl saturated solution, and EMF of the cell is plus 0.2422 volt. If the electrode is act as anode, oxidation reaction will take place. That means formation of Hz2 plus 2 electrons. If the electrode is act as cathode, the formation of Hz2 plus, and then the second step is the formation of Hz. In overall reaction as HgCl2 plus 2 electrons, this forms 2Hg plus 2 Cl minus. The electrode potential is given by E calomel, that is equal to E naught calomel minus RT divided by 2F ln AC1. That is the electrode potential. Next we have to discuss about EMF series. EMF series are electrochemical series, that means the number of electrodes are placed in the order of their increasing values of standard reduction potential on the hydrogen scale. Then the arrangement is known as electrochemical potential or EMF series. The significance is calculation of standard EMF of the cell. If the electrode potential values are known, we have to calculate the EMF of the cell by using this equation. E naught cell, that is equal to E naught RHE minus E naught LHE. In second is oxidation or reduction. Higher the value of standard reduction potential, greater is the tendency to get reduced. That means the reaction is oxidation reaction. Then lower the value of standard reduction potential, greater is the tendency to get oxidized. That means the reduction is oxidized. Third one, displacement of one element by other. Metals which lie higher in the EMF series can displace those elements which below them in the series. For example, hydrogen can be replaced by negative electrode potential values. In fourth one, determination of equilibrium constant for an equation. If the standard EMF values are known, you have to calculate the equilibrium constant. del G naught, that is equal to minus RT ln K. So from this, minus del G naught is equal to RT ln K. 1 ln is equal to 2.303 or log. That means log K is equal to minus del G naught divided by 2.303 RT. That means the log K is equal to NF E naught divided by 2.303 RT. Increase in free energy del G naught, that is equal to production of current NFE naught. So from this equation we have to calculate the log K. Hydrogen displacement behavior, that means metals with negative reduction potential, that metals can be used to displace hydrogen. Then sixth one is spontaneity of reaction. If the E naught of the cell is positive, the reaction is spontaneous. If the E naught of the cell is negative, the reaction is not spontaneous. Then we have to discuss about corrosion. So corrosion, that means metals or alloys generally used as a fabrication or construction of materials in engineering. If the metals or alloys are not properly maintained, they deteriorate slowly by the action of atmospheric gases, moisture and other chemicals. The phenomenon of deterioration or destruction of metals or alloys is known as corrosion. Corrosion is defined as the gradual destruction of metal or alloys by chemical or electrochemical reaction with its environment. Causes of corrosion. These are in metals occur in two forms. One is native state, second one is combined state. Native state, that means the metal occur in native. That means non-reactive with the environment. They are noble metals. For example, gold, platinum and silver. Combined state, except noble metals, all other metals are reactive and react with the environment, form stable compounds, their oxides, sulfates and chlorides and carbonates. These are the reasons for corrosion. Then causes for corrosion. The metals are extracted from the ores. During extraction, the ores are reduced to their metallic states. In the pure metallic state, metals are unstable. They are considered an excited state or higher energy state. Therefore, as soon as the metals are extracted from the ores, reverse process begins the metal compounds which are thermodynamically stable and lower energy state. Hence, metals are used in various forms. They are exposed to environment. The exposed metal surface begins to decay, conversion into more stable compound. This is the basic reason for metallic corrosion. Due to corrosion, some useful properties of metal such as electrical conductivity, ductility and malleability are lost. Then effects of corrosion. Due to formation of corrosion, product over the machinery, the efficiency of the machine gets lost. The products get contaminated due to corrosion. The corroded equipment must be replaced frequently. Plant gets failure due to corrosion. It is necessary for our design to compensate for the corrosion. Corrosion releases toxic products, health hazards, etc. Classification or theories of corrosion. Based on the environment, corrosion is classified into dry or chemical corrosion and wet or electrochemical corrosion. Dry or chemical corrosion, that means the attack of metal surfaces by atmospheric gases such as oxygen, hydrogen sulfide, nitrogen, sulfur dioxide, etc. There are three main types of dry corrosion. One is corrosion by oxygen or oxidation corrosion. Second one is corrosion by hydrogen. Third one is liquid metal corrosion. Oxidation corrosion, that means the attack of oxygen with metal at low temperature, low or high temperature also. In the absence of moisture, alkaline earth metals are oxidized at low temperature. At high temperature, almost all metals are oxidized. Mechanism of dry corrosion. The oxidation occurs first at the surface of the metal, resulting in the formation of metal ions, which occurs at the metal oxide interface. Metal that forms metal ions plus 2 electrons. Then oxygen changes to ionic form O2 O2 minus. Then third reaction is oxide ions reacts with metal ion that forms metal oxide film MO. That represents the metal oxide film. Once the metal surface is converted into mono layer of metal oxide, for further corrosion to occur, the metal ion diffuses outward through the metal oxide barrier. This is the diagram of metal oxide layer. The nature of oxide film. Nature of oxide film formed on the metal surface plays an important role in oxidation corrosion. Stable oxide layer. A stable oxide layer is a fine grained structure and gets adsorbed tightly to the metal surface. Such a layer impervious in nature and stops further oxidation corrosion attack. For example, aluminium, tin, lead, copper, etc. Unstable oxide layer. Unstable oxide layer is mainly produced on the surface of noble metals, which decomposes back into the metal and oxygen. Volatile oxide layer. The oxide layer volatilizes as soon as it is formed, leaving the metal surface for further corrosion. For example, molybdenum oxide. Fourth one is protective or non-protective oxide film. According to Pilling-Bedworth rule, if the volume of oxide layer is formed less than the volume of the metal, the oxide layer is porous and non-productive. On the other hand, if the volume of oxide layer is greater than the volume of metal, the oxide layer is non-porous and protective. Pilling-Bedworth ratio, that means the ratio of the volume of oxide layer formed to the volume of metal consumed is called Pilling-Bedworth rule. Then second one is corrosion by hydrogen. Corrosion, hydrogen embrittlement. That means metals contact to H2S at ordinary temperature, evolution of hydrogen. Fe plus H2S, this forms FeS plus 2H. Atomic hydrogen into molecular hydrogen. Then the atomic hydrogen diffuses readily, collects and form molecular hydrogen. H2. Collection of these hydrogen gases in voids develops the high pressure which causes cracks and blisters on the metal. The formation of cracks and blisters on the metal surface due to high pressure of hydrogen is called hydrogen embrittlement. Decarburization. At the high temperature, atomic hydrogen is formed by the dissolution of molecular hydrogen. When steel is exposed to this environment, the atomic hydrogen is readily combines with the carbon of steel and produces methane gas. Collection of these gases in the voids develop very high pressure which causes cracking. So the process of decrease in carbon content in steel, that is known as decarbonization of steel. Then liquid metal corrosion. This is due to the chemical action of liquid. Either dissolution of solid metal by liquid metal or liquid metal may penetrate into the solid metal. That is the liquid metal corrosion. Then second type is wet or electrochemical corrosion. This is due to the dissimilar metals or alloys are in contact with the in presence of aqueous solution or moisture. When metal is exposed to varying concentration of oxygen or electrolyte. These are the two reasons for electrochemical or wet corrosion. Then first one is hydrogen evolution type corrosion. All metals above hydrogen in EMF series have tendency to get dissolved in acidic solution with simultaneous evolution of hydrogen gas. When iron metal contacts with non-oxidizing acid like HCl and H2, evolution occurs. For example, Fe, this forms oxidation reaction. At cathode, liberated electrons flow the anodic and cathodic port. Hydrogen ions gets reduced to H2. Then absorption of oxygen or formation of hydroxide ion type corrosion. The surface of iron is usually coated with thin film of iron oxide. However, the iron oxide film develops some crack will come and anodic areas are created on the surface, while remaining parts act as cathode. At anode, Fe thus forms Fe2 plus 2 electrons. At cathode, formation of hydroxide will take place. The net corrosion reaction is Fe2 plus 2 OH minus. This forms FeOH2. That is the formation of hydroxide layer. This is the wet corrosion. Then the difference between chemical or electrochemical corrosion. It occurs only in dry condition. Electrochemical corrosion occurs in moisture. So chemical corrosion is due to the direct attack of metal by environment. Electrochemical corrosion is due to the setup of large number of cathodic and anodic areas. In chemical corrosion, even a homogeneous metal surface gets corroded. In electrochemical corrosion, heterogeneous surface or metallic contact as the condition. In chemical corrosion, corrosion products accumulate in the same place where corrosion occurs. In electrochemical corrosion, corrosion occurs at anode while products formed elsewhere. Chemical corrosion is self-controlled, electrochemical corrosion is continuous process. Chemical corrosion follows adsorption mechanism, electrochemical corrosion follows electrochemical reaction. Examples for chemical corrosion is formation of mild scale on iron surface. Example for electrochemical corrosion is rusting of iron in moist atmosphere. The types of electrochemical corrosion. There are two types, one is galvanic corrosion, second one is differential aeration or concentration cell corrosion. Galvanic corrosion, that means when two different metals are in contact with each other in presence of aqueous solution or moisture, galvanic corrosion occurs. Here more active metal act as anode and less active metal act as cathode. For example, zinc and Fe couple, in which zinc is more active, that means higher in EMF series, results in performance to ion, and less active metal zinc act as cathode. Anode undergoes corrosion. Fe act as cathode. For example, copper and Fe couple, in which ion dissolves and Fe act as anode and undergoes corrosion, Cu act as cathode. Examples for galvanic corrosion: steel screw in a brass marine hardware corrodes. This is due to the galvanic corrosion. Iron becomes anodic and it is attacked and corrode, while brass act as cathodic and it is not attacked. Second example is bolt and nut. These are made of same metal, so here there is no galvanic corrosion. Prevention: galvanic corrosion can be minimized by providing an insulation material between two metals. Then second one is differential aeration or concentration cell corrosion. This types of corrosion occurs when a metal is exposed to varying concentration of oxygen or any electrolyte on the surface of metal. Metals partially immersed in water or conducting solution is called waterline corrosion. If the metal is partially immersed in solution, the metal above the solution is more aerated and becomes cathodic. On the other hand, the metal part inside the solution is less aerated and it becomes anode. At anode, metal undergoes metal oxide, metal ions and 2 electrons. At cathode, formation of hydroxide ions will take place. In factors influencing the rate of corrosion. The rate and extent of corrosion is mainly depends on the nature of the metal and nature of the environment. Nature of the metal, that means position in EMF series, then relative areas and of cathodes and anodes, and then corrosion is depends on the purity of metal, other voltage, over voltage or over potential, then nature of surface film, then nature of the corrosion products. Nature of the environment, that means corrosion is directly proportional to the temperature. Then humidity, that means the rate of corrosion will be more when the humidity of the environment is high. And third one is presence of corrosive gases. The acidic gases like CO2, SO2, H2S, fumes of HCl and sulfuric acid produces electrolytes which are acidic and increases the electrochemical corrosion. Presence of suspended particles like NaCl and ammonium sulfate along with the moisture act as powerful electrolytes and thus accelerate the electrochemical corrosion. Then effect of pH. Possibility of corrosion with respect to the pH of electrolytic solution and electrode potential of the metal is corroded with the help of 4-box diagram. Rate of corrosion will be maximum when the corrosion environment is acidic. pH is less than 7. Then control of corrosion. Corrosion controlled by sacrificial anodic production or impressed current cathodic production. Sacrificial anodic production method, that means in this method the metallic structure to be protected is made by cathode connecting with it by some more active metal, so that all corrosion will concentrate only the active metal. The artificially made anode thus gradually gets corroded, protecting the original metallic structure. Hence, process is otherwise known as sacrificial anodic production. Applications of sacrificial anodic production. This method is used for the production of ships and boats. Sheets of magnesium or zinc are hung around the hulls of the ship. Magnesium or zinc will act as anode compared to iron. So corrosion concentrates zinc or magnesium. Since they are sacrificed in the process of saving iron, they are called sacrificial anode. This is the diagram for ship production. Then second one is impressed current cathodic production. In this method, impressed current is applied in the opposite direction of corrosion. Current nullify it and corroding metal converted from anode to cathode. This can be done by connecting negative terminal of the battery to the metallic structure to be protected, and positive terminal of the battery is connected to the inert anode. Inert anodes used for this purpose are graphite, platinized titanium. The anode buries in a backfill. The backfill provides good electrical contact to anode. Applications of impressed current production. Structures like tanks, pipelines, transmission line towers, underground water pipelines, oil pipelines, ships, etc. can be protected by this method. This is the diagram for impressed current cathodic production. The comparison between sacrificial anodic method and impressed current cathodic method. Here there is no external power supply. In impressed current method, external power supply must be present. Here this method requires predicted replacement of sacrificial anodes. Here anodes are stable and do not disintegrate. In sacrificial anodic method, investment is low. Here investment is high. Soil and microbiological corrosion effects are not taken into the account. Soil and microbiological corrosion effects are taken into the account. In sacrificial anodic method, this is the most economical method, especially when short-term production is required. This method is well suited for large structures and long-term operations. In sacrificial anodic method, this method is suitable when the current requirement and the resistivity of the electrodes are relatively low. In impressed current cathodic method, but this method can be practiced even if the current requirement and the resistivity of the electrodes are high. Thank you. In next class we have to discuss about energy sources. Thank you all.